Hello and welcome everybody to Advent of Code 2023, day 11. So today was a pretty nice problem. Wasn't too difficult. I'm very proud to say that the difference in code between my part 1 and part 2 is pretty much nothing. Just one variable needed to be changed in value to get the answer for both parts, which is pretty cool. That's always a bit of a win, and the performance differences between the two is pretty much negligible. So that's pretty cool. It doesn't happen that often. When it does, it's always a nice feeling. So the problem itself isn't super complicated. There's an approach that I decided to take which made it pretty straightforward. I think it's a relatively clever approach. There's probably simpler ways you could do it, but breaking it down this way, I thought it reduced a lot of what I perceived to be the complexity of the problem. So with all that said, let's have a look at our problem, and yeah, let's jump straight in. So, day 11, Cosmic Expansion. So, we're wandering along in our metal world, and we encounter an elf. So we come upon an observatory, and we encounter an elf inside it. He says he doesn't know anything about machine parts, but he'll show you how to get to the hot spring. But he has to finish something first. So he's doing some cosmic analysis. So he's looking through his telescope and he's taking pictures of the night sky. The picture of the night sky is our input. And basically the deal is he wants to try and figure out the shortest paths between the galaxies that he's captured in his picture. So this is our input. We've got dots and we've got hash marks. So the hash marks represent the galaxies and the dots represent empty space. So using this, you need to parse this and we try and figure out what the shortest paths between all of these galaxies is on this grid. But there's a slight wrinkle. He says that the universe has expanded between taking this photo and doing the analysis of it. So if we want to get the actual answers, we need to expand the universe of our input. But he says that in our rules, the space only expands in certain places. And specifically, it only expands where you've got a completely empty row or a completely empty column of space in our grid here. So he has that indicated here by these arrows. So if you go down the length of this way, only this will expand outwards in our expansion logic, and the same for the vertically. So x's and y's will only expand in those empty regions. We're told that it expands to make it twice as big. So effectively, if we're going through this, if you were to make this grid yourself, you would have to, at some point when you hit there, you'd have to like insert a whole new row or a whole new column beside it, and that would become a new part of empty space, doubling the size of the space. And yeah, that's about it. Yeah, so the only other thing he says down here then is, so this appears to me to just be a left to right, top down thing where he's numbering each of the galaxies. And then what he says is you want to get the distance between all the unique pairs of these, of which there's 36. So it's the distance between 1 and 2, distance between 1 and 3, blah, 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 so on and so forth. And then the distance between 2 and 3, 2 and 4, so on and so forth. So you get the picture. There's 36 pairs. You find the shortest distance between them all, add them all together, and that's going to be the answer to our problem. Yeah, so that is the whole problem statement. Before I get into how I did it, a couple of things to note. So, firstly, you definitely don't have to create a 2D array and stick all the values in. The input gets quite big, so that might not work very well here. It's a very sparse data set, so a sparse data set works really, really well for this dictionary hash mapping of the data that I so love to talk about. And then the other thing, that's the other trick you need to know, is that you don't have to simulate walking between the 2 points. You absolutely don't have to do that. And the reason being, they basically tell you in the text here that the shortest path, there's basically a straight line path between each galaxy. It doesn't matter if you pass through another galaxy, that's fine. That doesn't matter at all. And because we're on this grid, they also say that you can only move left, right, up, or down to get to there. So because of that, we can leverage this Matt's trick called the Manhattan distance between any 2 points, which is on a grid where you can only move in those directions. The shortest path between any 2 points is going to be the sum of the difference in the x's and plus the sum of the difference of the y's. So that is that basically if you were imagined that we were going to walk this, it's every x move that we did, then plus a y move, then plus an x move, plus a y move, plus an x move, plus a y move. That will give you your answer. You think about that. If it doesn't make sense to you, maybe straight away draw it on a piece of paper and just like count the dots, and then subtract the max and the min x value, the max and min y values, get their absolute values and add them together, and you'll see that it works. So Manhattan distance, and don't put this all in one big grid, and we'll have a great time. So with that said, let's have a look at the code, how I implemented this. Okay, so first thing I decided to do was to create a map hash, which is going to be the main data structure that's going to store all of our points of our galaxies. And then I have these 2 other arrays, and the purpose of these 2 arrays is to basically determine which index of x's and which index of y's is going to be a blank row. So the way I populate this is, let's see now, I go through my file, I go through every line and then go through every character of every line. So I'm basically going to populate these 2 arrays. If an array index is empty, I'll stick a value in there, which could be a dot or it could be a hash. And then I don't stick any other values in if I've seen a hash in there already. So what this will give me at the end is this will give me an array that's got everywhere in the vertical or in that horizontal line, everywhere that there is a galaxy, there'll be a hash symbol, and then every index that has nothing, either vertically or horizontally, because I'm doing it twice, will have just a dot in it. So that's how I determine that that's a region of space that needs to be expanded based on the index of that array. Then I can put in the galaxies into the map, just check where there's a hash, stick it in, and then I increment the galaxy index just so that I get my so I can do my unique pairing later on for the distances. Now this is the real meat of what we're actually trying to solve, which is the expansion logic. So if you get this logic right, then the problem is trivial after this. This is just a little bit you might need to think about. So for me, I do 2 loops, 2 identical loops, one that expands the x's and one that expands the y's. You could do this in one loop and do them at the same time. I just thought it was clearer for me in my head just to implement it once and then just duplicate it. So basically what we do is we go through that array that we had earlier of the hashes and the dots. As we loop through it, we skip all the hashes and we're only interested in the dots. Yeah, that's right, Kat. We're only interested in the dots. Good girl. So when we encounter a dot, we'll go through this. So basically what we do now is we go through our map of all of our points and we check that the coordinate, that the x coordinate in this case, isn't greater than the index that we're on, which is the index for the first expansion, basically. And if it is, then we know that we need to increase that x coordinate. So we basically need to pad that x coordinate out by the amount of the expansion. So the expansion amount is 1. Now, the reason I ended up coding it like this is actually, it works super well, but the only reason I ended up coding it like this is because originally I did it wrong. I had for some reason in my head, I was like, it needed to be 3 times as wide. So I added in a variable just to make that clear, and then I realized that was wrong, and then I needed to test it, so I changed the variable value a few times to make sure I had it right. I misread the problem, but it ends up being fortuitous here. So anyway, that's just set to 1 for now. And then the only other little trick in here is that as you expand the universe here, all the other points down here all get bumped out. So now the index of the next piece of empty space is actually bumped out further. So that's what this expansion amounts counter kind of, that's what that takes care of, being able to bump out the next index so that you can do this test and it'll still work. And that's it really. This will expand out your universe. So all this does is the data structure hasn't changed at all. All we've done is we've just updated our X and then our Y coordinates of our map inputs. The map has stayed the same size in memory. It's just the values in them have changed slightly. And yeah, so that's it. We've expanded out our universe. And now the very last bit, we need to just figure out the shortest distance between all the pairs. So I just did a lazy thing here, 2 nested loops. I created a hash of pairs, which I'll store all the uniques in. The way I get that is I just take the 2 IDs, I'll join them in a string with a colon, I'll sort that, and then just check that for uniqueness. So in this case, 1, 0 will end up being the same as 0, 1, which means we don't recompute that distance because it's a unique pairing that we want. So you'll end up with your 36 unique pairs in here. And then the distance is super simple. We take the X, we take the 2 X values, we get their difference, we take the absolute value of that, and we add that to the difference, the absolute difference of the 2 Y values, sum that together, and that's it. That's our answer. So then the final answer then is the pair values, and you sum them together, and that's it. So we can run this if we go. So if we run it on our sample, that's the correct answer for the sample. Runs in 2 milliseconds. We'll run it for our input. It's a little bit slower, 1/5 of a second or 1/4 of a second. And yeah, that is the correct answer. So let's move on to part 2 then. So for part 2, basically, they say that the galaxies are a lot older and then much further apart than they initially seemed. And effectively, the only thing you have to do here is you're just increasing that expansion distance. So it says that instead of them being twice as wide, the expanded space, it's actually 1,000,000 times larger. So now you'll see why I said don't use a grid for this, because if you were able to do this with a grid, now you're not able to do it with a grid anymore. So now we expand our space by 1,000,000 times, and I think you know exactly what we're going to do for that. So if we go to our code, second part, it is literally identical except for this one variable here, the expansion amount variable. Yeah, everything else is literally exactly the same. And the expansion amount is 900,099, blah, blah, blah. And yeah, and that works. So if we run, actually he's a little cheeky. He doesn't actually tell us what the answer for the sample should be in its full amount, but he tells you what it should be if it was 10 times and it was 100 times. So you can test that. So for the, so that's part 1 still. So for part 2 on the sample, he tells you that you don't actually know that that's an answer, but he does tell you for 100. So if we change that to 99 and run it for the sample, it's 8410, which is the sample answer for 100. So just keep scaling this up, and you'll get the correct answer. So I'm going to run it for my input, and there's our answer. And the runtime is basically identical to the last runtime we did, and that should make sense because we haven't actually changed the processing of the problem at all. We still do the same amount of iterations of the same loops. We just have a little bit of difference in the values of the arithmetic, and that's it. So that's it for day 11. I thought this was a nice problem. I really enjoyed doing this one, and yeah, let's see what tomorrow brings. After yesterday, this was a welcome relief because yesterday absolutely demolished me. So yeah, I'm pretty happy with this one. And it was a little bit of fun. So I hope that helps someone. I think those 2 little optimizations, just knowing the Manhattan distance and not doing this in a grid, make your life a hell of a lot easier for this one. So yeah, that's it for now. I will see you guys tomorrow.